Under normal conditions, every user request travels from the application directly to the primary database. The database processes each query independently and returns fresh data every time. When traffic is low, this design appears simple, reliable, and completely acceptable. The problem begins when thousands of users request exactly the same information: product details, user profiles, or feed content. The database receives identical queries repeatedly and rebuilds the same result again and again, wasting CPU, connections, and input-output capacity. As the repeated work grows, connection pools begin to fill, CPU usage spikes, and query latency rises rapidly. The database becomes saturated. Every new request must wait behind earlier requests, turning the database into the main scaling bottleneck. Users now experience response times of around 300 milliseconds or more. Pages load slowly, interactions feel sluggish, and some requests begin to time out. A backend resource problem has become a product problem that reduces trust and throughput. Redis solves this by adding a fast, in-memory cache between the application and the database. Frequently requested data is stored in memory, while the primary database remains the source of truth. Redis does not replace the database. It prevents the same answer from being rebuilt for every request. The application now follows the cache-aside pattern. When data is requested, the application checks Redis for the cached key before touching the database. A cache lookup is extremely cheap compared with a database query. When a value exists, the expensive database read is skipped entirely. This is a cache hit. Redis already has the requested value in memory and returns it in only a few milliseconds. The application sends the result to the user, while the database performs zero work for this request. This is the fast path that keeps latency predictable. This time the key is missing, so we have a cache miss. The application must query the primary database for the authoritative result. Cache misses are expected after a cold start or expiry. The important step is what happens after the database returns the value. The application writes the fresh result into Redis with a time to live, then returns the response to the user. One database read can now prevent thousands of future reads. A single cache miss prepares the system for many fast cache hits. The next user requests the same key. Redis now has a warm copy in memory. The flow becomes user to application, application to Redis, Redis back to application, and then to the user. No database query is required, so the response becomes nearly instant. Time to live prevents cached values from living forever. When the countdown reaches 0, Redis automatically removes the key. The next read becomes a cache miss and refreshes the value from the database. TTL balances faster reads with acceptable data freshness. When the underlying data changes, the application must invalidate the cache. It first updates the database, which is the source of truth, and then deletes or refreshes the old Redis entry. Without invalidation, Redis may continue serving stale information. What happens when Redis is unavailable? The application uses a short cache timeout and safely falls back to the database. The cache is an optimization layer, not a reason for the entire service to fail. Circuit breakers and controlled recovery protect the database during degradation. Compare the two paths. Without caching, every repeated read reaches the database and may take hundreds of milliseconds. With a warm Redis cache, most reads return from memory in only a few milliseconds. The exact gain depends on network, payload size, and cache hit rate. Here is the complete cache-aside journey. On a hit, the application reads from Redis and returns immediately. On a miss, it reads from the database, stores the result in Redis, and responds. Writes update the database and invalidate the cache. Together, these paths provide performance, freshness, and resilience.